We are going to do what is essentially the last example we're going to do. We're going to do it two different ways. Hopefully today we'll make it all the way through the first way. We're going to do it sort of the chapter 8 way first, the full doing the whole problem way. And then I'm going to show you how to do it with tables on Wednesday, which is way easier. And I may have time, we'll see. I also solved this problem in Mathematica, so I showed that as well. So like there are lots of ways you could do it in Mathematica. I did it a long manual way in Mathematica, but there are simpler, more automated ways as well. So that's something that I may just upload, and I think that there might be one more example that I uploaded for your notes, but do just have that for reference. So, without further ado then, we will begin this. So this is actually 9.23 in your textbook, the problem. Notice it's in Chapter 9. We're going to use Chapter 8 methods because that's totally valid. Given the vibration, I modified it a little bit, but given the vibration isolation table model right here, what is the unit step response of the velocity of the mass for a unit step input of the base here? We will use methods of Chapter 8. So the mass is like the vibration isolation table. A lot of times these vibration isolation tables have like a large, massive tabletop. And then the support structure is has a little bit of, has a stiffness associated with it and some damping. And then through the floor, let's say, there's some velocity input. And we want to see what happens if there's a unit step input. Just sort of for the hell of it to see if what's going to happen with the system as it responds. So we'll solve this problem, and we're going to do step response. So this is we're going to find an input-output differential equation. We're going to solve it. So what we're going to do, our method is going to be make a state model, turn that into an input-output ODE, and then take that input-output ODE, solve it for the output as a function of time. So that's what we're going to do. So let's do it. There's a lot of work, but I thought it would be kind of nice to put it all together since the last week we'll do a problem where we put it all together in one problem. So let's draw the linear graph, a normal tree.
You should pick a positive direction in the...
Oh, I like the way you're thinking. So should we go this way? Because it'll make the signs work out nice. So if we choose that as our positive direction, this is our ground. The mass is definitely going to have a node. And then this also has a separate velocity as well, right? Because this moves independently from ground. So two non-ground nodes. One of which is connected to a velocity source. And which direction should that velocity source arrow point?
Down.
Down. Excellent. Vs. And it's down because we're in the direction of the coordinate arrow with our velocity source. That's exactly right. And then we have between this node and the mass node, we can draw in the mass, which always points to ground. Between the source node and the mass node, we have a spring and a damper, right? So K and B. Okay. So what's our normal tree? Velocity source, because it's an across variable source. What? A types, which is the mass.
And we can't take any more because that make those.
Right. Any more would make a loop, so we're done. which is great. So we could do our primary, secondary variables, but since we're getting so used to this, we could just maybe skip right down to state variables. What are our state variables going to be?
VM.
VM, because the cross variables of A-type energy storage elements in the normal tree.
And T-types
And
that are.
spring.
Yeah, so through variables of T-types not in the normal tree. So the force through the spring, which is a T-type, not in the normal tree. So what is the order of the system? 2. So our state vector is going to be, let's choose VM and then FK. And our input vector, it's good to also define. What is that?
Yes.
Yes, very good. All right, so we're just moving right along here. No issues so far. Elemental equations, let's draw our nice little column here. M, K, B, those are our 3 elements. And what is the elemental equation for the mass?
dVm dt equals
1 over M.
1 over m.
FM.
Yeah,
Take for a second.
it's F equals MA, but it's rearranged so that A equals 1 over MF. I am using dot notation in this problem. Yay for dot notation. What about for the spring? Hook, right? Derivative of Hooke's law. Time derivative of Hooke's law.
KBK.
Yeah. Fk dot equals K BK. And Fb equals BVB. The Fb here is the primary variable because it's not in the normal tree. So it's already solved as we would like it to be. Continuity equations, how many do we need? Two, right? Actually, do we need this one?
No.
No. We only need the one. Way to catch me. So continuity equation says that Fm, the force on the mass, is equal to Fk plus Fb, right? And compatibility equations, how many do we need? 2, 1 for each of these links, right? So if we put the K link in, we would get that Vk equals Vs minus what?
PM.
Good. And what is Vb equal to?
Same.
Same thing. Very good. Excellent. Now, step 6, we'll do some algebra. Let's draw our little column again, because it's always nice to do. So, M, K, B. So, we have Vm dot equals 1 over M. Fm, which is just Fk plus Fb, right? And the Fk dot equation, Fk dot equals K Vk, which we know is just Vs minus Vm, and Fb is equal to B times Vs minus Vm, right? So we have now eliminated all secondary variables. And now is the part where the algebra can be tricky, but in this case is super easy because we just have this one equation for a primary variable that is not one of our state variables, and we just plop it into this first one. So let's just kind of cheat a little bit and write this in line here. So 1 over m. Fk is a state variable plus b vs minus vm. Boom. And we have our state equations. All we need to do is write them in standard form. So let's go ahead and do that. X dot equals, A is going to be a what by what?
2 by 2.
2 by 2, multiplying X, which is Vm, a 2 by 1, Fk, plus, what is the B matrix? 2 by 1 times U, which is a 1 by 1. And what is this first line? We'll use this first equation. So Vm dot is equal to, so the Vm coefficient is negative B over m, very good. And the Fk is what? Just 1 over m. And what about the Vs?
Just B over M.
B over m. Is there anybody who is at all confused about that process? Because now would be pretty clutch time.
Last time. This is your last chance.
It really is. Speak now or forever hold your peace.
What
We've been doing this a long time.
we had a test on it.
Yeah, you're right. You guys, that test was on the challenging side, but you still averages like a 63. It's not that bad.
That's a and you dev saver, that's like great.
Yeah, that's not bad at all. The last one average was like almost 80, wasn't it?
It's too good.
That was really high. So they averaged to like somewhere in the 70 range, which is perfect. So it's not that. I'm pretty happy with the grade so far. You guys might not be, but you have an opportunity on the final exam to really just give your grade a little boost at the end. I actually think that the final exam, you guys are going to surprise yourselves at how well you do on the final exam. There cannot be a problem harder than the problems that you got on the second midterm. Those are literally like the hardest problems that you could have gotten in this class. So, yeah. There's really nothing, I mean, what have we done since then? We've learned how to transform into transfer operator, system transfer operator,
The H stuff.
and the H stuff, and then change that into a differential equation and solve those, which we already did. So, I mean, it's really, there's not that much new stuff. And so those problems that you got on the midterm were about as challenging as you could possibly get.
So we're not going to do anything with the transformer and the non-net.
Well, I'm not saying that,
And
but
diodes.
but if you can do those problems on the midterm, you could do that, right? So, yeah. Oh, we accidentally started talking about the final, did we?
You did.
The length of the final, so it's a 2-hour exam, right? So I mean, the midterm, second midterm was a little on the longer side, so it'll probably be longer than the second midterm exam for sure, but it won't be a ton longer. Because you were a little bit compressed on the second midterm, I'm going to really be careful to make sure that you have plenty of time on the final, so that some people don't work well under a time limit like that, and so I want those of you who struggle with that aspect to have a good opportunity on the final exam to show how you understand things better. So yeah, I'm gonna give some material longer than the second midterm, but it won't be a ton longer than the second midterm. So yeah.
It's like 5 questions.
Yeah, it might even be shorter than that. Yeah, I mean, because some of these problems take some time to go through, right? So, yeah. So we'll see. I mean, there are parts to the problems. I mean, like usually I ask some like direct questions, like write a short sentence or two about it, and so there's like A, B, C, D, or so whatever on that. And then the other problems, I mean, I do ask like A, B, C, D, E, F, G usually or whatever, but usually I'm walking you through the problem, right? So I could just ask for the final answer.
I like your method better.
Yeah. But I realize some people on the test freak out and they're like, I can't remember the first step, and then so I ask them like the first step and then the second step.
scaffolding or something?
Yeah, I could believe that. Yeah. Okay, so what do you guys think about the FK dot equation?
You've already got it, basically. It's and 0.
Wonderful. Super easy, right? And then we need to write our output equation. So this is the part where there can be confusion sometimes. So I'm going to slow down for a second. Our output, in this case, we care about Vm, right? So I say I want to know what the step response is, Vm. So we want to know what the velocity of the mass is. So Vm is our output. We could write, if we wanted to really just be very careful, we could say, okay, y1 is equal to Vm. Okay? Now, we need to write whatever that output is in terms of state variables and inputs. Conveniently, Vm is a state variable. So that's pretty great. Chase, we need a chase cam, I swear. Okay, so we just need to select out the state and input. Well, there is no input that we're going to use, but what is the dimension of the C matrix?
1 by 2.
1 by 2, right? 1 output, 2 state variables. So 1 by 2 multiplying Vm Fk, the state vector, plus a, what is the D size?
1 by 1.
1 by 1. And writing this equation in this form, we have, what is the coefficient of Vm?
1.
1. What is the coefficient of Fk?
0.
Vs? Wonderful. Bam. Okay. So now we have a state model, which is great. We could go to MATLAB and simulate this response, the step response. We could do that. We've learned how to do that. But instead, we're going to solve it out analytically. Okay. So the state space to input-output differential equation process occurs through the transfer operator, right? And that has this formula, H is equal to CSI minus A inverse times B plus D. What does this mean?
Yeah.
So this was the definition of the system transfer operator. And these are, so the A, B, C, and D matrices are this A, B, C, and D matrix.
Oh.
Yeah, right?
Oh, I'm back.
Yeah. And then S is the derivative operator, differential, and I is the identity matrix, essentially, that makes this a diagonal of S's.
Is that all being integrated because it's not negative 1?
This is an inverse, because these are all matrices, so this is a matrix inverse. But as I said, we only need to be able to do up to a 2 by 2 inverse by hand. I'm only requiring that in this class. So on the final exam, you should be able to do a 2 by 2 inverse, and we're going to do one right now. So you're going to get an opportunity to see it done again, because we already did it once. I know, it's almost becoming boring. We're just doing the same thing over and over again. Not boring yet? Okay. By the way, I have been writing up that lab that we did. I don't know if anybody's been paying attention. I keep updating it. So much interesting stuff in that. Like, I realized after I put it all together that, like, I mean, you could almost do a whole class on that one lab. Like, there was so much cool stuff happening in it. So, anyways, more you can read. You can read what I write about it on.
Interpret backwards data.
Backwards data, yeah. Is it backwards?
Yeah.
So I saw one of the group's curves came out real nice, real nice. So this time of year, I start to quote Eddie, cousin Eddie. Cousin Eddie. Do you guys know?
I'm uncultured.
Yeah, it's the Christmas Vacation movie. You gotta watch it. National Lampoon's Christmas Vacation. You know that the Abbot really likes National Lampoon's movies? I haven't had many conversations with the Abbot, but that was one thing that came up in conversation. I thought it was pretty awesome. So, okay, so what we need to do is, so over on this side, I'm going to compute the green stuff, okay? Because I think that instead of rewriting this whole thing over and over again, it's easier just to compute this separately. So let's do that. We've got, so SI is going to be a, I'm not going to put the little serifs on the S's because it's kind of a pain. 0, 0, S. So that is SI. And that can be whatever size your A matrix is. So our A matrix is a 2 by 2. So if this was a 3 by 3, it would be all zeros except for 3 S's along the diagonal. Minus A, our A matrix that we just wrote up here. So I'll just copy that down. Negative B over M, 1 over M, negative K, 0. So I want to compute the inverse of that. So that is equal to the matrix inverse of S plus BM, B over M, right? So it's element-wise. Subtraction and addition of matrices is just element-wise. 0 minus 1 over M is just negative 1 over M. And 0 minus negative K is just positive K. S minus 0 is just S. And we're taking the inverse. And I told you guys that the formula for this shows up in your textbook in the appendix, but it's pretty easy. So what you do is you divide, so you have to divide by the determinant. So there's a constant out here that is the determinant of this matrix. You guys remember how to compute the determinant? Yeah, so this times this minus this times this, right? So that's going to be S squared plus, distributing the S here, plus B over M S plus K over M. Right? Times, and then the matrix we multiply this by is, do you guys remember, you flip these two and you change the sign on the other ones. Is that right? Am I right in remembering that? 'Cause sometimes I forget, I have to look it up. Yeah, I think that's right. Let's see what my notes say. Yeah, that's right. S plus B over M and negative K and 1 over M. It's funny because I can't look at my notes very closely while I lecture, otherwise like it just feels like I'm just copying things down, which isn't really very helpful for you guys, I don't think. And so I usually just do these problems live in front of you, and I just check them occasionally. So that's why we're prone to error. So this right here is all the green stuff, right? That's why we did it in green, because we're like third graders. Okay. Now we need to take C times that and B and multiply that by B. So our C matrix, let's do that right here. Our C matrix is 1, 0, right? 1, 0 from up here. C matrix times this whole thing. This constant, this denominator here, I'm going to define this to be something. Why don't we call this denominator we'll define it to be delta. Okay? So times 1 over delta times the matrix S 1 over M negative K S plus B over M times B, which, come back up here, is this vector here, well, 2 by 1 matrix, B over M and K. And we're going to add to that D, which is just 0, right? So that'll be easy. So the 1 over delta, this is all a constant, well, it's a scalar. I shouldn't call it a constant. It's a scalar, right? So we can pull the scalar out and do the matrix multiplication. So let's do this times this first because there's a 0 in there and a 1, so it's super easy to do. I'm going to knock some stuff out, and then we'll do the second one. Okay? So that we could do it either direction, but. So 1 over delta comes out front. We're going to have, this is a 1 by 2 times a 2 by 2, so what are we going to end up with? A 1 by 2, right? So the 1 by 2 is going to be S plus 0, so S, and then 1 over M plus 0, right? Which is 1 over M. Well, that simplified. Times B over M K, which, this is a 1 by 2 times a 2 by 1. What are we going to end up with? A 1 by 1. That's right. That's also very nice. Real nice. It's a quality item.
Could you go over that part on the second part? You multiplied the C by B.
This part?
Yeah.
Okay, so I pulled the 1 over delta out. And then I had a 1 by 2 multiplying a 2 by 2. So the inner dimensions collapse, and I'm going to end up with a 1 by 2. The first element of which is going to be this row with this column, right? So 1 times S plus 0 times negative K. And then the second element's going to be 1, so this row and then this column. So 1 times 1 over M plus 0 times this. Yeah. And we're still left with this. So now this is just also known as the inner product or dot product. Right here, we just have S times B over M. So we have B over M S plus K over M. Right? So what we've got is H equals, I will write it out in all of its glory. Since this is a 1 by 1, we're just going to drop the matrix notation. And we're just going to say this is B over M S plus K over M divided by, so this is the delta part, S squared plus B over M S plus K over M. So we have our system transfer operator. Now, the next step is to go from the system transfer operator to the input-output differential equation. Recall that the output is always equal to the H operator operating on the input. Right? That's the definition of it. And our output, single output, is just VM, right? It's equal to H, which is this, operating on VS, the input. So B over M S plus K over M, S squared plus B over M, S plus K over M, all of that operating on Vs.
Is that multiplication?
So, if you recall in the lectures on operators, we discovered that you can actually treat these as algebraic variables. However, interpretation-wise, we should be careful to recognize that they are in fact operators. S is in fact an operator, and this is actually a polynomial operator. We defined the polynomial operator. However, you can manipulate these polynomial operators in the same way that you manipulate algebraic equations, and so an algebraic expression. So we can just treat it algebraically and just think about multiplying both sides by this denominator, for instance. But really what we're doing is we're operating on both sides by the inverse of, by this polynomial operator, which is on this side cancels out as an inverse operator, and over here operates on Vm. So it is important to recognize that there is a distinction between operators and simple algebraic and arithmetic relationships, but they do operate in the same way. They're effectively, you can treat them the same and it all works out.
Okay, I'm just wondering if we're given an input Vs, how would we use all that stuff on it to get our Vs?
Yeah, we haven't learned how to actually solve anything in this form yet. We just thought about it in terms of operators. We can draw block diagrams for it. We will learn how to do that next semester. But for now, we're just using it to transform into an input-output differential equation. And that is what we're going to do right now. So you could think about this as multiplying both sides by this denominator, or you could think about it as operating on both sides with the inverse of this operator. So whichever way you think about it, you end up with if I was to write it in a more operatory way, heartburn.
Have a tongue.
Yeah, right. Fortunately, I'm too young to have that be a sign of a heart attack coming on or something. Eyes are watering a little bit. Okay, so this is, we technically could be writing this as this is operating on Vs, right? But this is the same as if we had considered this to be algebraic and multiply both sides by the denominator, right? Okay. And we can, these operators are distributive, right? So you can distribute the Vm so that you have S squared operating on Vm and plus B over M, B over M, S operating on Vm plus K over M, just the scaling operator operating on Vm, equals B over M S operating on Vs plus K over M operating on Vs. And yeah, so now you can actually interpret these back to how we initially defined these operators. So S squared is what in terms of calculus operations?
It's a second
D
derivative.
squared VM dt squared.
Exactly. Or in our case, Vm double dot, second time derivative. Plus, this is a mixture of a scaling operator and a derivative, which is equivalent to just b over m Vm dot plus k over m. A scaling operator is just multiplicative. So, word of the day, multiplicative. Vs dot plus k over m Vs. Whew! Alright. Now we have ourselves a good old-fashioned input-output ODE, right? Just what we always wanted. Our very own.
All around Christmas is an
It just sort of rolls off the tongue, doesn't it?
just like marijuana.
So, what we want to know is what the step response is. So we don't care. So we're putting in 0 initial conditions. So set them to 0. And here's our step input. Now notice we've got a derivative of the input here in this differential equation. Have any of you ever encountered that? In any of your classes? You might have. You may have. I don't know if they cover it.
But we know how to take the derivative of that step.
We do. So you could go that route. But here's another possibility. We are going to find the step response of this. So we're going to set the entire right-hand side of the equation to be just a step input. Okay? So if this was just a step input, we can solve that differential equation pretty straightforwardly. Then we can use a mixture of superposition and the differentiation rule to find the output for this, because this is a linear time invariant differential equation, right? So therefore superposition applies, and if Vs is a step input and we know what the step response is, we can, so if we were to cover up this part for just a moment, if we had k over m times Vs, you found the step response, how would you find the response to k over m times Vs, times the step? Just multiply, right? Because that's what superposition says. If you scale the input, just scale the output. Superposition also would say if you have two inputs,
You can add them together.
you can do them separately and add them together. And Vs is so this second input is a scaling of Vs dot, which is the time derivative of the step input. So we could just take the time derivative of the output of a step response and get what the response would be and add them all up together. It's going to be beautiful. Okay, so our general goal, our general strategy here is to solve for the step response and then use superposition and the derivative rule to construct the solution based on this input. Does that make sense? This forcing function, this right-hand side we call the forcing function. Vs is the input. We're going to say, okay, this whole forcing function, we're going to set it equal to the unit step input, and then we're going to use superposition. Because Vs is a step input, and we can construct using superposition what the output would be for that. Are you guys following that? I'm seeing some people look a little confused.
You're just trying to find the factor that Vs dot does on the output, then using whatever that factor is in times you use like Vs to get it.
Yeah, so we'll get there. You know what we'll do? Why don't we solve it for US to start, we'll solve it. We'll find what the output is for unit step input, and then we'll actually do the superposition stuff, and I think it'll become a little bit more clear at that point. So I was hoping we'd be able to see to the end here, but at least we'll be able to look forward. This is like we have the idea that we're going to use the unit step response once we know it to construct what the response is with this forcing function. Okay, and we'll get to that in a little bit. But for now, we need to come up with the step response with the right-hand side set to the unit step. So the homogeneous solution, this is just good old-fashioned differential equations, right? Characteristic equation, lambda squared plus b over m lambda plus k over m equals 0. And solve this for lambda. It's a quadratic equation, so lambda is equal to negative b over m over 2. I like to split it up into a real and potentially imaginary component. Plus or minus 1/2 times the square root of b squared over m squared minus 4k over m. Now, we have to know, in order to finish this solution, if this comes out to be an imaginary number, or a real number, or what, or 0, right? We need to know that because we're either going to have a complex conjugate pair of roots, or 2 real roots, or a repeated root. We need to know that for our solution. So we actually are going to plug in the numbers. And that comes out to be, so I gave you b, k, and m. They come out to be negative 1.875 plus or minus j 6.82. Okay, so what is our situation? Complex conjugate pair. And can we tell if this system is stable or not? Can we tell?
From that chart that you gave us.
Yeah, that's what you need to be looking at exactly. So what was the requirement for it to be stable? The roots of the characteristic equation needed to be in the left half complex plane, meaning that they had to have negative real parts. And so we have ourselves a negative real part here, don't we? Therefore, it's stable. And if we had a 0 real part, what would we have? Yeah, we call that marginally stable, right? It's a marginally stable system. And if we had a positive value here for the real part, it would be unstable. And we're gonna watch what happens with these roots of the characteristic equation, how they play into our final solution here. And it's going to be really interesting to see. It's going to be very obvious that if this was positive, it would be an unstable system. Yeah, so physically constructing an unstable system isn't actually that hard, but it depends on how you do it. For instance, an inverted pendulum is an unstable system. So if you perturb it a little bit, it'll crash. So that's one. But it's also nonlinear. A Segway is an example. Yeah. Yeah. It's just cool. Yeah, so that's a really fun control problem, actually, is to create an inverted pendulum and balance it. So like you could walk up to it and like knock it to the side and it catches itself. It's pretty cool.
That's not a project.
Yeah, it's a pretty fun one. That would be a fun project. It'd be really fun.
Senior project.
Also be a good senior project.
Are you teaching that class next semester?
Robotics and automation, I am. Okay, so our homogeneous solution then is, so Vm homogeneous of t is equal to C1 e to the lambda 1, so there's a plus side and a minus side, right? So e to the, I'll do the plus side first, negative 1.875 plus or minus j 6.82 t plus C2, sorry?
Is it C2 T E to?
No, we don't need to put in a t here. Why is that?
Because our lambda is 0.
Our lambda isn't a repeated root, so this term isn't 0. So if this j term was 0 over here, then we would have a repeated root. Then we would need to put a t here. But since this is plus, this is minus, there are two different, distinct roots. So e to the minus 1.875 plus or minus j 6.82 t. And so we could draw, here's our complex plane. We've got a negative real part of negative 2 and then plus 6. So,
what do you differentiate between one being plus and minus?
oh yeah. Good point. This one is the plus one, and this one is the minus one. It doesn't really matter. You can choose whichever one to be.
It's either or.
But you're right. You gotta choose. You gotta
Why
choose.
not?
Absolutely. We cannot be agnostic on this point. We really do need to choose. So here's where our poles are, and they're, so like we said, they're stable because they're in the left half plane. They are also off the real axis. Therefore, we're anticipating what sort of unique aspect of our response? A damped oscillation, that's right. It's going to oscillate, and it's going to damp out because it's stable. If it was over here, it would be oscillating and increasing in amplitude. And if it was right on the axis, then it would be oscillating and never damping out. So we're expecting a damped oscillation here. But a pretty oscillatory system because we're pretty close to this axis. We're only negative 1.875, so it'll definitely have some oscillation associated with it. Okay, so we will pick this up on Wednesday and learn another method as well for how to solve this problem.